We now find the electric potential at a point due to distributed charges, which could be many point charges, or it could be a charge that's over some volume. So let's first take a more than one point charge. So let's suppose you have a charge Q1 here and a charge Q2 here. What's the electric potential at this point P? There is no charge over here. In order to get potential energy, we would need to have a charge here. But for the electric potential, there is no charge here. Every charge has a potential field around it. And so we want to find the electric potential over here due to these two charges. Similar to an electric field, which would be here, when there's no charge, it's just a point in space. So if this distance is taken as R1 and this distance is R2, then the electric potential at the point P is the potential due to the charge number 1 plus the potential due to charge number 2. And these are not vectors, so we just add the two up. Now V is KQ over R, so that's KQ1 over R1, and this is KQ2 over R2. And we can write it like this. Now if there are more than this many charge, all we need to do is, if there are several charges, then this is simply the sum of KQI over RI, where I would be 1, 2, and 3, 4, whatever number of charges. And that will be the potential due to a number of charges at some given point P. Now, if you don't have a few discrete or distinct point charges, but we have a cloud, okay, so there's a region of space where there is some charge, and the charge may be more concentrated here, it may be less over here, so different places may have different charge densities. And we want to find the electric potential at the point P. So we can go by what we did before and say that, okay, we'll divide this into a number of parts, and we can say that the charge in this whole region is concentrated here, and that's Q1, and the charge in this region is concentrated here, we call that Q2 and Q3 and Q4 and so on. So we'll have a large number of point charges which sort of represent this entire cloud. And then this distance would be R1, and this would be R2, and similarly for all the others. And then the potential would be the sum of KQI, or we can, QI over RI, the same as what we had before. Now, to improve the accuracy, we need to divide this into a large number of smaller volumes. So then we'll have tiny little volumes, and the number of volumes become very large. So if the charge in this little volume, which we call it as delta Q in the ith volume, so in the limit, when the delta Q tends to 0, then the summation of K delta Q over Ri will become the integral of K dq over R. And we do the integration over the entire volume of that cloud. So this becomes the equation that the potential at a point P is the integral over the volume of K dq over R. The point P could be inside the volume. It could be a point over here, or it could be outside. Now we will use this equation and this equation to solve some examples. So the first example that we take is if we have a number of point charges. So we have 2 point charges. One is plus q, the other is minus q. They are placed on the x-axis. The distance between them is 2a. So this is a and this is a, and we want to find the electric potential at a point P that is on this axis, which is equidistant from the 2 charges. And so R1 and R2 are also equal. This thing is called a dipole if the 2 charges are equal. So if we want to find the electric potential at P, we'll say it's the sum of VI, which will be the potential due to 1 and the potential due to 2. This is KQ1 over R1, KQ2 over R2. If this is a positive charge and that's a negative charge and their magnitudes are equal, so Q1 is Q and Q2 is minus Q. So we replace Q1 with Q and Q2 with minus Q, and R's are both equal. Well, this will just cancel out. And so the potential along this line is 0. So this side has positive potential, this side has negative potential because it's minus. We put a negative over here, so the potential here is negative, here is positive, and along this line it's 0. If the 2 charges were not equal, we would still have a line somewhere, it might be curved, where the potential would be 0. Now let's find the potential at the point R. Okay, so we found it here, now let's find it here, along the x-axis, closer to the negative charge. So again we have the potential is given by KQ1 over R1, so that's the potential due to Q1 at here, and then the other one due to Q2 over here. And Q1 is Q and R1 is from here to here. That's going to be X, which is where the point is, R, and plus A. So it's X plus A, and from here is going to be X minus A. So Q2 is negative Q, and this is X minus A. And then we can take the K and Q outside. We'll have 1 over X plus A minus 1 over X minus A. And then we have the LCM and X minus A and X plus A. The X's will cancel out, and we are left with 2A. And A plus X and X minus A, X plus A is here. And so that becomes the potential at the point R. KQA over X squared minus A squared. Okay, so it's going to be KQ times A divided by X squared minus A squared. Now, if the point R is very far away, so that X is very large compared to A, or in other words, if Q1 and Q2 are very close together, they're very close to each other, so that the A is small compared to the X. So X is much greater than A. This A remains, but this A becomes negligible compared to X squared. We can remove that, and we're left with this equation. That gives us the potential due to a dipole very far away, but on the side of the negative charge. Now let's take another example, and this is if we have a distributed charge. So we have a rod that is of length L and very small diameter and uniform charge density. The total charge is Q and it's distributed uniformly over the length. So we have a charge per unit length, or the linear charge density would be the total charge over the total length. So this will be the linear charge density, and it's going to be coulombs per meter. So every meter length of this rod would have so many coulombs. That becomes the linear charge density. Now to solve this, we break this up into a large number of small elements, and then we perform the integration. So one of these elements is here, and its charge is delta Q. The thickness or the length of this is delta X, and it's located at X. So the delta Q comes from here, the charge density times delta X. The charge density is Q over L. So if we know the charge and the length, we know lambda, and so we get delta Q is a known value times the delta X. So now the potential at P due to this charge is going to be kq over r. So k is constant, q is delta q, and r is this. So it's going to be kq delta q over r. R is given by a square plus x square square root, so it's Pythagoras theorem. That's x square, and a square equals r square. So we substitute r is this value over here, and the delta q is lambda delta x over here. We get k lambda delta x over here, and then we do the integration over the entire length, and so we will integrate this, and the limits will be from r equals a to r equals this whole distance. Or since we're doing it in terms of delta x, the delta x will go from 0 to L. So this equation becomes, that's the same thing again, integrated, and the k and lambda are constant, and we have dx over a plus x square square root, and x goes from 0 to L. Now this is constant here, and the integral of this term is ln x plus a square plus x square square root, and the limits are 0 to L. So when we substitute the limit L, we get this. Substitute the limit 0, we get this. So this is just simply ln a. Ln of this minus ln a would be ln of this divided by a. So that becomes the equation for the potential at the point P over here. Now, if we have a situation where we want to find the potential above some other point, if you want to find it here, well, you can consider this to be one rod and apply this equation, and then you can consider this to be a second rod and apply the same equation. So this will be L1, that will be L2, there will be Q1 and Q2. Well, lambda may be the same in both of them. So you can apply that by breaking this up into two parts. Now let's find the electric potential at the point R, which is here along the axis of this rod. So this is the charged region, and we are at a distance a from it. So we have the same equation for a point charge. Sorry, the equation for the potential will be the integral of kq over r. The dq or delta q is lambda delta x, and r is the distance from here to any point, and we can take that as x. So now we can start our x equals 0 would be here, and then we integrate from x equals a to x equals a plus L. So now instead of taking x equals 0 here, we take x equals 0 here, and then this point is at a distance x from r. So we get this equation, and then the integral of dx over x is ln x. Apply the limits from a to x plus a plus L. So the limits are from x equals a to here, and substituting these, x a plus L minus ln of a, so it becomes a plus L over a. That becomes the potential at the point R. We now take the case of a charged ring. So we have a ring that's empty in between. It's just let's say a metal ring that has a charge capital Q on it, and this charge is uniformly distributed over the entire ring. Then what is the electric potential at a point on the axis of this ring at a distance x from the ring? The radius of the ring is a, and this distance is r. So we take V equals kq over r, and k delta q over r, and r is again a square plus x square square root. So it becomes a square plus x square square root. Now as we integrate, we take this as a little element delta q. As we integrate here, the r at every point will be the same. So r here will still be a square plus x square square root. So r remains constant. And so it can be taken outside. So now the k is outside and the r is outside. We're left with the integral of dq, which is simply the total charge q, and that becomes the electric potential at the point on the axis a distance r from the ring. Now, if you want to find the electric field, we can find it as a rate of change of voltage. So the electric field is minus dV by dx. And so if we differentiate this with respect to x, we get d by dx of this equation, and the dx is taken outside, so d by dx of this, and that becomes minus half this thing as it is to the power 1 more than this, minus 1 more than that, and the derivative of what's inside, so that gives us 2x. The 2's will cancel, the negatives will cancel, we'll get kq times x over this, and which is the same as what we had earlier.